Hello everyone, let's solve maximize alternating sum using swaps. So we have an array and we want to maximize nums0 minus nums1 plus nums2 minus nums3, etc, etc. And we are allowed to do some swaps. So for example, for the first example, if we don't do any swaps, we do 1 minus 2 plus 3, which is 2. But there's a better way of doing it. If you swap 1 with 3, you get 3, 2, 1, and then you can swap 1 with 2 and you get 3, 1, 2, and 3 minus 1 is 2 plus 2 is 4. So that's the optimal way. Right, so using the swaps you can have a bigger sum. And we are looking obviously for the maximum sum. We can do any swaps in any order, and we can do any of those swaps any number of times as well, which is important. So we're looking for something in a linear complexity because nums can have up to 10 to the power 5 elements. And so the key to solving this problem is to notice that if we have an array and some swaps, instead of writing down a list of swaps, we can just think of those swaps as edges between indices of an array. So we have a graph. The nodes would be each index of this array, and each edge would be an allowed swap. So for example, if I'm allowed to swap 0 and 2, 2 and 4, 4 and 5, and maybe I'm also allowed to swap 1 and 3, 3 and 6. Right, that would be the graph I would have. And you can see in this graph, we have sort of two connected components. And within those two connected components, because we can do any swaps any number of times and in any order we want, we can basically, within any connected component, we can swap everything as many times as we want. So we can rearrange things as we want. So for example, in this connected component, maybe I don't want to change anything because this is a plus, minus, plus, minus, plus, minus, plus. So I already have the big values in plus and already have the small values at minuses. But in the second component, let's pick another color. In the second component, in the minuses, I have 2 4s, and in the plus, I only have 1 3. So we probably want to trade 1 4 for 1 3. I guess swap, not trade. And so what I'm saying is within each connected component, we are going to try and do something greedy. Put the big values in pluses, put the small values in minuses. If we only have pluses or only have minuses, we can't do anything, obviously. The core of the work will just to find those connected components. And we could use DSU, but I feel like we don't have to. We can just run a simple algorithm that finds connected components, right? Just run a bunch of DFS, very standard algorithm. So I guess that's pretty much it for how we solve the problem. When we want to put the big things in pluses and the small numbers in minuses within a connected component, what we'll do is we'll put all the values of a given component in an array. So here we would have 2 arrays. We would sort those arrays, and whenever we encounter a minus, we put the first ones, and whenever we encounter a plus, we put the last one, and we do this walking through the component. Right? So we do many time sorting operations, but each of those sorting operations will be n1 log n1, n2 log n2, and n1 is the size of the connected component number 1, n2 is the size of the connected component number 2, So if we sum all those complexities, we end up having something like nlogn, which is still fine. Right, so it's okay to have many sorting operations because we actually sort on sort of small subsets of the initial array. So for the complexity, we'll end up having something like nlogn, but it will be much easier to see how things work when we look at the code, because the code is very simple. So for the code, the first thing to do is to create our graph. So I said in this graph, there'll be as many nodes as there are indices in num. So let's create our adjacency list. And then we said each swap would be an edge. So swaps, for uv in swaps, graph of u, dot append v, graph of v, dot append u. And now that we have our graph, we want to look for the connected components. Connected components. So I'll do a DFS search of the connected components, but you could use DSU. So we have a visited list, put false everywhere. We could obviously use a hash set, but an array will be slightly faster. We will have our list of connected components that we want to deal with afterwards. So each sub list in a list here will be the list of indices that make up one connected component. And so we run our standard connected components algorithm. For each of the nodes, if it's not visited, we run a DFS. And component is initially empty. We have a stack for our DFS. We could run a BFS as well. We didn't change anything. Look through on the neighbors. The neighbor is not visited. We add it to the stack and we mark it as visited. And then when the stack is empty, it means we've explored the connected component, and we can just say connected components dot append our component. And notice that we add indices in node and start, which is I. All of these are indices of the graph, because the graph we're building has for its nodes the index in nums. Hopefully that's clear. So that's the connected components part. Find all the connected components and store them. And now we need to greedily swap things within each connected component. So greedily sort and assign values within each connected component. Our answer will be 0. We'll eventually return the answer. And for each component in connected components, we want to sort, but we can't sort component directly because component is a list of integers, each integer being an index. So I guess we first create component values, which is a list of integers, which will be nums I for I in component. We sort those values, and we'll put greedily the small values at odd indices and the big values at even indices. So first we need to count how many odd indices we have. So odd indices count. Right, if the bit representation of the number ends with a 1, it's an odd number, so we add 1, and we have the number of odd indices component. again, each of those loop takes n of k. We have m connected components, and the complexity will be the sum over all m connected components of those nk, which will be n, because the sum of all nks is n, because in each component, you never have a node that ends up in several components. Obviously, you also have the sorting complexity, right? I'm just saying for this loop, even though we have nested loops, it's not a problem, right? And it's the same here. We have nested loops, but as you know, for the finding connected components algorithm in the graph, it's still big O v plus e. And v here is big O of n, and e is the number of swaps, but the number of swaps is at most 10 to the power of 5 as well, so we're good. Everything is linear in v and e. So that's why I'm not worried at all, even though there are nested loops. So now that we have the number of odd indices, well, the first odd indices count values in component values will be assigned negative, and the remaining will be assigned positive values, right? So basically put at odd indices the small values. So answer will be minus equal component values all the way up to odd indices counts, and answer will be plus equal component values from odd indices count to the end. And yeah, that's pretty much it. Small values set at even indices. Cool. Let's check if I haven't made any typos. I did. Oh yeah, this is still a list. I want to minus equal the sum of everything in that list. That's my bad. All right, let's try now. All right, the test case is passed, so we can try and submit. We get 4, 2, and this big negative number, which is what we expect, and it gets accepted. So nlogn time complexity and big O of n for the space complexity. Right, again, this is a list of integers, but it's the same. It is going to be something like sum of nk for k from 1 to m, which is n, and m being the number of connected components, because each node is in at most one connected component. So no worries, big O of n for space complexity.